Yeah, please start.
Okay. Okay. So my plan is, at least for today, initially I'm just going to spend some time reviewing whatever Raghavan has talked about in the last 3 lectures, and probably adding a few points here and there. And towards the end, my goal is to sort of talk about the symmetric Mcdonald polynomials. Okay, so again, feel free to stop me if if I'm going too fast or what I'm saying is not too clear. Uh, so to broadly summarize the theme of what we have done so far, um, the starting point is really the what we call the affine while group of GLN, or the maybe extended affine while group. So this is what Raghavan talked about in the previous lecture. So this is as an abstract group. This is just the semi-direct product of the lattice Zn with Sn. But it's more useful to think about two of its actions. So there are these two standard actions of this group. So the first one is sort of familiar if you've seen affine root systems and affine while groups and so on before, which is that the group W acts on the lattice Zn as follows. So there are two things we need to say. So one is, if you take an element of Sn, how does it act? So Sn acts just by permuting the coordinates. This permutes coordinates of Zn, and given an element of Zn, how does it act? So the action of an element of Zn we denote by T sub mu, T for translation, and T mu is just translation in the usual sense of the word. So this just takes, let me dispense with the underscore here. So this is X in Zn. So it just translates by mu. Okay. So this is the standard sort of action. This is how one thinks of affine while groups in general, as acting on the lattice. But the other action, which is what Raghavan talked about last time, is an action on Z itself. Okay. And this action is via what was called n-periodic permutations. Okay. And the definition of the action is as follows. So what is an n-periodic permutation? It satisfies the following property, that W acting on the integer I plus n is determined once you know W on I. It's just Wi plus n for all I in set. Okay. So there is an action of W on the set of integers where the elements act as n-periodic permutations. And the way to think about this is as follows. So you look at the set Z and think of it as sort of a collection of n abaci and so on. Okay, so there are these n abaci, if you wish. So each is numbers congruent to 1 mod n, 2 mod n, and so on. So there's 1, 2, 3, all the way till n, and then n plus 1, n plus 2, etc. Sorry, minus n plus 1, and so on. And what is this permutation, n periodic permutation? What does it typically do? So it permutes the abaci among themselves. In other words, it's sort of you grab one of them and you sort of permute its position. You move it somewhere else, but when you move it there, you're also allowed to sort of slide it up or down. Okay, so there are sort of these two sorts of things you can do, which is on the one hand, you can just permute the abaci themselves. So that's sort of how elements of Sn act. So here are the actions. So if I take an element sigma in Sn, it just acts by just permuting the abaci. Permute the abaci without any sliding, okay, without sliding up or down. So that's the elements of Sn. And then the elements of Zn, how do they act on the abaci? Well, they perform a pure sliding without any permutation. So this is, so remember mu in Zn is a tuple of integers, mu1, mu2, mu_n. And the action of this element mu, or what we call T mu, on the integers, T mu acts by sliding the first abacus by, so ith abacus, up by the amount mu I. Okay? And of course, if mu I is negative, you're actually going down. Okay, so these are just the pure slides. They're just going up or down along each of the abaci. And an element of Sn, all it does is it permutes these abaci without actually performing any sliding. Okay, so this is more or less what we talked about last time. And so there is.
Can I just take a look at the previous slide just for a second?
Sorry, go on.
Can I take a look at the previous page just for a second?
Yes, sure.
Okay, so the notation is going to be, we'll just work with that.
I'm sorry, what?
That's all. Thank you. That's
all. Okay. Okay. So this was the action on Z. So moral of the story so far is that the affine while group has these sort of two nice actions, if you wish. So the other important thing, I mean, you can sort of identify the two of them as well, but let me just go on to the other thing that Raghavan talked about, which is you can talk about the generators of the affine while group as follows. So there are these obvious SIs, the generators of the finite Sn portion. So you have S1, S2, Sn minus 1. So these are just the transpositions in Sn. But then there was this additional element which you call pi. And what does pi do? So pi is an element of W. It's best to think of it in terms of its action on these n periodic permutations. Its action on Z, it's just given by pi just increases all numbers by 1. Okay, so this was our definition of pi. And so for example, if you perform pi n times, so what is it in terms of the abaci, if you wish? So pi just does the following. It moves everything along except the very last guy is sort of moved to the first abacus, but with one step above it. Okay, so and so on. So now you can see that if you perform pi n times, what you're actually doing is just translating all abaci one step up. So pi power n, for example, is just the translation by 1. Okay, now two other notions which maybe not sure Raghavan talked about them, just length. So length of an element W, again in this n periodic, I mean in terms of its actions on Z, the length is just the number of inversions in the usual number of inversions of W, which again means the number of that is the number of pairs I less than J, such that Wi is bigger than Wj, except that now here I and J both run over all the integers. So this is going to be an infinite set. If it is non-zero, it's automatically infinite because you will be able to periodically find pairs. So you sort of restrict I. You only pick I's from distinct conjugacy classes. So let's pick, this is I mod n, if you wish, or let's say you restrict I to only run over 1, 2. Okay, and J, of course, can vary. So the length is going to be just the number of inversions in the usual sense of the word. And so let's call this L of W. So observe now, this number can be, the length can be any positive integer, I mean 0 or positive. In particular, the element pi has no inversions because this last element n here is actually mapping to n plus 1. So if you sort of look for inversions, you will see that there aren't any. So the length of pi is in fact 0. And in fact, there are lots of other elements of length 0. So I think this came up at some point when we are wondering if it was a Coxeter group and so on. So there are in fact infinitely many elements whose lengths are 0. In fact, lots of translations have length 0. So for instance, so what's a translation? If I take, if I move each abacus up by some amount, as long as I translate the first abacus by an amount which is smaller than what I translate the second abacus by and so on, then I'm going to actually get, so observe length of t mu in particular, I mean, you can actually write out a formula for it if you wish. It's how much you translate the first minus what you translate the second, but you only keep this if it's positive. Okay, if it's negative, then you just put a 0 there. So mu1 minus mu2, sort of the positive part, plus mu2 minus mu3, the positive part, and so on. So this sort of tells you what the relative, I mean, you can see that you will get those many inversions if you slide the first abacus up by more than what you slide the second abacus up. Okay, so the length of a typical translation looks like this. And so when I put plus, I mean, it is, you keep it if it's positive, or replace it by 0 if it is negative, if the quantity inside is negative.
I have one question.
Yes.
Yeah. So for why basically after restricting only I from 1 to n, why this set becomes finite?
With set because of the way it acts, because of the so for each I, you want to know how many,
the set which defines length of W.
Correct. So you're asking for a given I, why are there only finitely many J's for which this can happen?
So okay, we already have this W of J is strictly less than W of I. All right. Yeah. So I got it.
Okay. Yeah, I mean, because after a while it's just that plus n, right? So it's eventually going to become, Wj's will become bigger than Wi eventually.
Yeah.
Okay. So the length of a translation is this, and so from there you can see that for a translation, for instance, to have length 0, all you want is to just take it in increasing order. So length of a translation, for example, is 0 if and only if the mu's, the corresponding mu, is in weakly increasing order. Okay. So
sorry, that feels funny to me.
Oh, is that right?
If I translate the last abacus just up by 1, then the n goes to 2n, right? But 1 goes to 1. So n plus 1 goes to n plus 1, and so I get an inversion at the position n. Somehow I'm confused. I feel like if I consider t sub 0,0,0,0,1, then that has some positive length.
Oh, I see. So there is, between the last abacus and the first one, there is a problem.
Yeah,
right?
Because the last abacus would move the dot up by n, and the first one wouldn't move it that far, so that would cause an inversion. Yeah, somehow it feels funny. In my mind, the length 0 elements are pi to the k.
No, but length 1, the n was already to the right of 1.
Correct. N was already to the right of 1.
Right? So I think it's okay. If it
no,
was
but n plus 1 will map to n plus 1. So n will map to 2n, and n plus 1 will map to n plus 1. So n plus 1 is an inversion.
N plus 1 is an inversion. I see what you mean. Okay. So I guess there's something wrong with this. Is there a general formula for the length of a translation in terms of?
In my memory, it's the absolute value of mu I minus mu j, summed over all I less than j.
Okay. Let me just write that down and maybe we'll figure this out. So length of T mu is.
Is it true that this length coincides with extended affine while group length? Like that we get it from as extension of affine while group. In that case, length 0 elements only will be corresponding to the Dinkin diagram automorphisms.
Correct, except that's in the affine wide group. I mean, of SLN, right? I mean, this in some sense seems like GLN. So I'm sort of a little confused by this length business.
But I think the length 0 elements are the powers of pi.
They're just the powers of pi?
Yeah.
Okay. Okay,
Yeah.
good.
So then that is finite.
No. It's
not
still infinite
finite.
in this case.
Yeah.
So
Sorry.
let's just record that. Maybe we do that as a tutorial thing. So length of W is 0 if and only if W is a power of pi. Is that right?
I think so, yes.
Okay, sounds good. Okay, so let's come back to this. So maybe I should say this now. Okay, so so the thing I wanted to say was that S1, S2, Sn minus 1 and pi generate. So that was the key point of this, that these are generators. They generate W, and in some sense, I mean, it's enough to just show it for the translations alone, because the finite portion is already generated by S1, S2, Sn minus 1. And so in fact, all you need to show is that d mu can be written in terms of these guys. And so I noticed that in the tutorial sheet from last time, there was this computation of this special word for t mu and so on. So given a t mu, so you can try to write it as a word. So a t mu can be written as a word in S1, S2, Sn minus 1, pi and the pi inverse as follows. So what you want to do is, so observe that, because of the way the pi is defined, it sort of moves the last abacus to the first one by translating it up by 1. If you wanted to get a translation, so this is something which Arun showed us during the workshop in December as well. So this is what he calls the box greedy word. For t mu, which is, so how does one try and do it? I mean, let's just do it by example. So if you take mu to just be, say maybe 1, 2, 3, and so that just means the first abacus moves up by 1, second by 2, and the third by 3. You want to realize this in terms of as a word in the SIs and pi. So you sort of just perform the following algorithm. So just start at 0, 0, 0. So observe pi is the only guy which can increase the number of the total sum by 1, for example. So if you start at 0 and if you apply a pi, then this will go up by 1. So you apply a pi, this becomes a 1, 0, 0. Now, so the next thing you do is you push the 1 down to the end. So you have to apply S1, S2. That pushes it to the end. Then you again apply a pi. So it goes up by 1 again. Now you push the 2 to the end, again by the same process. Apply a pi again. So you've gotten your 3. This is all right so far, Arun? The box greedy.
Sorry, what is 0, 0, 0?
No, so that's your starting point. So just imagine, so these are just imagine you're translating. So these are the translations of the 3 abaci. So initially you do nothing.
Aha.
When you perform pi, what you're doing is you sort of are moving the last abacus to the first position and translating it up by 1. So we are sort of keeping track of what we're doing by.
Right, but the t of, you had said that pi changes I to I plus 1 for every I, right?
That's right. But in terms of the abaci, when you think in terms of the abaci, it was moving the last abacus to the first and translating it up.
Okay, thanks.
So in some sense, that's what this is. If you really think of this is the first abacus, second abacus, and third abacus. Okay, I mean, one should actually also keep track of that eventually. So this is the first abacus, second abacus, and third abacus. Then when I apply pi, the third abacus is sort of moved to the first place, but it's gone up by 1. Okay, it's been pushed.
The other 2 are just translated, but not pushed up, not pushed vertically.
I'm sorry, say that again.
The other 2 abaci are just translated horizontally, but not vertically.
Yes, they are translated horizontally, but not vertically.
Okay, thank you.
Okay, so then you sort of push this first guy all the way to the end. So now this is the third abacus. the first and the second guy is here. Then you apply pi again. So the third fellow is sort of moved here, but moved up by 2 units. The first and the second are here. Okay. So and so on. So we're just keeping track of the abaci and the respective translations, the sliding. Now, so you keep going like this. So we've gotten the 3, and then you then try to get the next guy. So the 3 is done. You try to get the 2 next, and that you do by just the same process. So I again start at the end, make that into a 1. Okay, and then push the 1 all the way to the end. So that's 3, 0, 1. Apply a pi again. It becomes 2, 3, 0. And then finally apply pi again. You get 1. Okay, so there is this. So the intermediate steps are always these sort of sliding words, the ones which take something the first position and move it, not necessarily all the way to the end, but to wherever it needs to go. I guess all the way to the end. Okay, so so this is what called the box greedy word. But observe what you've gotten at the end is not necessarily t mu. Okay, so what you've gotten at the end is the right amount of translation, but you may still not have moved the correct abacus. In the sense, if you kept track of which abacus is where along this path, you'll notice that the end may not exactly be the first, second, and third abacus. So, for example, this was a third, first, and second, and then this translation, this is the third, the first and the second are still here. This is the third, the first, and the second. So second, third, first, the third, first, and second. The second, the first.
Yeah, in this case, it's correct. In this case, this is.
In this case, it's all correct because it was, I guess, in increasing order. Yeah, absolutely. So if it is an increasing order, in the end, it will turn out to be, the right abacus in the right places. But that's not always true. For example, if mu was just 0, was 1, 0, for example, the way you get it from 0, 0 is by first. So this is the first abacus and second abacus. You'll just apply a single pi to get a 1, 0, but then the abaci are in the wrong order, right? This is, you have translated the second abacus by 1 unit and the first by 0 units, but that's not really what you wanted to do. So in some sense, you still need to act by an S1 in order to get the abaci in the right places. So this is 1, 0, but then when I apply an S1, sorry, what happens? The first abacus moves to the second place, so that.
So do you have pre-applied S1?
Sorry, I'm sorry, what?
Should you have applied the S1 to start before pi?
I have to apply S1 before pi. Absolutely. Thank you. Absolutely. So if I did that, then I would get them in the right order. Okay. Maybe I should just. So okay, let me just write the answer. So T mu, in some sense, is not pi in this case, but rather pi S1. Okay. So so anyway, so the point is, in general, you can do this, but from this, this came up again. This comes up when one actually constructs the Mcdonald polynomials. So those u mu's. So finally, this expression gave. So T mu, what we have just done, this box greedy and so on, is you have produced an element u mu, which is what we did along this process. Okay, you try to write it in terms of, you start with 0, 0, 0 and get to mu by applying a sequence of pi's and si's. But once you do that, you may still be off by some finite Weil group element, off by some element of the Sn. Okay, so T mu can be written like this, where what are the properties of u mu and v mu? So let me just remind you of this. Where U mu is nothing but the minimal length element of the finite, the coset T mu Sn. Okay. V mu has another property. It's of course an element of Sn, which has the following property that, well, it's the minimal length which maps mu to mu in increasing order. Okay, so you rearrange mu in increasing order, weakly increasing order. The element which does, which does that. There may be many of them if mu has repeated entries, and you pick the minimal length element. So V mu is exactly that element of S. Okay. Okay. Now, so this was the first. So these elements finally made an appearance when we constructed the Mcdonald polynomials, what Raghavan talked about. Now, so this is about the affine while group. Now, I just wanted to briefly mention something Raghavan maybe didn't talk about, but it's sort of there nevertheless. This is the double affine while group. So, what's the double affine while group? Well, we sort of do the same thing twice. What we just did. So we take two lattices. I mean, you take two copies of Zn in this case. We call one of them as L and the other as L check. And let's do the following. We construct a new group as follows. So it's got Sn, in some sense, Sn semi-direct product L. So that's going to be, that's the affine while group. But on the other side, we'd also put L check. So there's also going to be another component, Sn semi-direct product L check, if you wish. And so, I mean, the semi-direct product, so maybe I can write it like this. So think of it as a group which is generated by the generators of Sn and by the lattice, such that Sn and L, they interact via the semi-direct product relation. The same with L check. And the L and the L check that you have defined, they together with the central element form a Heisenberg group. So what this means is that, let me just try to write this out very quickly. So the double affine while group, if you wish, is, well, maybe as a set, I suppose. It's just Sn cross lattice L, then there's a lattice L check, then there is a central element. So just as a set, it's this. And what's the group multiplication itself? Sn cross L. This is like, here the group multiplication is like the semi-direct product. Okay. Similarly, Sn with L check, the group multiplication is like the semi-direct product. Okay. L and L check themselves are abelian groups, where the group multiplication is the usual addition on lattices. And L and L check, they interact as follows. So if you call a typical element of L as, so we'll write them as x to the mu's instead of just mu's. Let's look at x to the mu and y to the, so we'll call them lambda check. So what are mu and lambda check here? Mu comes from L, lambda check comes from L check. Okay. So these two elements, they commute past each other, they move past each other as follows. You move them like this, but then you incur a term which is q to the mu lambda check. Okay, so it's sort of a central extension. You have these two lattices, and the group action here is, you've got this central extension. Okay, so it's these two alone, they form a Heisenberg group. So this structure is what we call a double affine while group of GLN. So again, this has an alternate presentation, just like, observe, this is like an affine while group part, but as we just saw, an affine while group can also be obtained in terms of, these generators S1, S2, Sn minus 1 and pi. Okay, so let me just quickly draw the other picture for the double affine while group, an alternate presentation, if you will. So you've got the generators S1, S2, Sn minus 1.
Sorry, can you go to the previous letter 1 second?
Yes, sure.
It's slow today.
This one?
Sorry, I have a quick question. So this inner product is the usual dot product?
Yes, yes. So in this case, it's a usual dot product on Zn because both are just Zn. So I mean, this setting is somewhat more general. You take a lattice and it's dual, and so for other root systems as well.
Okay, thanks.
This is the group. Yeah, this is the Heisenberg group version.
This is the Heisenberg group corresponding to that.
Right. Okay, this is just the dot product. Okay. And can you go back to the previous slide with the U and the V?
This one?
Yeah. Thanks. Sorry. I'll just, yeah.
Okay. Okay. So, so I was going to say that there is this alternate presentation, which is you take S1, S2, Sn minus 1, and the affine while group part, Sn semidirect product L, corresponding to that, there is going to be so corresponding to that, there is going to be this additional element that we call pi. Okay. Now, there is a pi for this, but I'm sort of going to silently slip in a check there. So there is this set of generators. So this bit here is like, I mean, these are the generators of the affine while group Sn semidirect product L, and the things here are, again, they form an affine while group corresponding to Sn semidirect product L check. And of course, you still have the Q. Okay, and this, I mean, we would probably have morally thought of calling this as a pi rather than a pi check, but so I'm just doing this to sort of retain consistency with the. There seem to be good reasons for wanting to do this when one talks about intertwiners also. Okay, so so this is the double affine while group, the picture of the generators. Now the next thing that one talked about. So the key thing in all this, of course, is that there is one can sort of relate these two affine while groups via involutions and so on. So maybe we'll look at that during the tutorial. But let's quickly move on to the next thing Raghavan talked about, which is the double affine Artin group. So this is sort of what you get when you Artinize or do the braid group version of what we just talked about. And so recall there that the double affine Artin group corresponding to this collection of generators, the corresponding Artin group generators are T1, T2, Tn minus 1. And so the way we talked about this, there were actually two generators on top, S0 check and G check. Okay. And if you remember what the Artin group relations were, they were, they corresponded to this diagram here, okay, which just says that these satisfy the braid relations. But we also had the other relation that G check conjugates each Ti to the subsequent Ti. So G check, for example, would conjugate Tn minus 1 to S0 check. Okay, and it would conjugate S0 check to T1. Okay, so and the others likewise. But the reason I'm pointing this out is S0 check itself, therefore, is sort of a redundant generator in some sense. So in this point of view, we can just choose to say, well, S0 check itself is, well, I mean, this equation here defines S0 check, if you wish. And these two relations can sort of be rewritten by saying that G check Tn minus 1 G check inverse is just the same as, we just put the checks on the other side. This is just G check inverse. Okay, so these two are actually equal to check, and each of them is what we're calling S0 check. Okay, so I can sort of delete S0 check from this and just think of G check alone as my other generator. Okay, so of course the reason for wanting to keep the S0 check morally is that I suppose in other root systems and so on, you may not have this, or even in the case of SLN, if one chooses to work with just the root lattice of SLN and so on, you may not have this additional element availability. Is that right, Arun?
Yes, that's right. Yeah.
Okay. Okay. So in this case, we do have this element. So let's just choose to dispense with S0 check and think of the generators as being just T1, T2, Tn minus 1 with G check. And again, the double affine Artin group means we also have a corresponding G on the bottom. So this is T1, T2, Tn minus 1. So here is sort of an affine braid group or affine Artin group. This is another affine Artin group. And then there's this additional element Q, which is central. Okay, and what one has in some sense is if you wish, the analog of the Heisenberg relations, except it's in terms of G and G. So okay, let me not get into the relations and so on. So we've got a bunch of relations. The key thing here is that these two affine Artin groups are sort of related by this involution. So there is this involution I at the group level, which does the following. It takes G check to G and it maps each of the TIs to their inverses. So it sort of maps. And Q to its inverse. Okay. So this is the presentation of the double affine Artin group in terms of just a single generator G and G check on top. But just like we had for the double affine Weil group, one can replace the G check by this entire lattice. Okay. So I mean, we could do it at the level of Artin group, but let me again quickly move on to the Daha, where we have the same sort of picture. So the next thing that Raghavan talked about was the double affine Heka algebra, which is, well, it's just the Artin group in which you impose some relations on the TIs. Okay, so this is just the double affine Artin group, the group algebra of the double affine Artin group modulo the relations, the usual Heka relations on just the finite TIs. This is only on the T1 through Tn minus 1. Okay. Now, so again here, what are the presentations themselves? So here, let me just say, we have the following presentation. Maybe I should say presentation. So let's say the first presentation of the Daha is again corresponds to the presentation of the dark that we just talked about. So I've got the T1 through Tn minus 1. There's a G check, there's a G, there's a Q. So same as dark, except there is some sort of collapsing here. In the sense Ti square is written in terms of Ti and the identity. Okay, so the Heka relations here sort of lead to some collapse among the TIs in the group algebra of the dark. So this is the first. So when I say collapsing, this is of course relative to the dark itself. So this is the first presentation. These are the generators, and we have a bunch of relations. But let me just quickly draw the other diagrams as well. So this presentation number 2 that Raghavan talked about, which is you take the T's and replace the G check on top. So keep the G as it is. Okay. So this. So by the way, this is an affine Heka algebra. This is the affine Heka algebra of GLN. So you keep that as it is, but replace the G check on top by the corresponding lattice generators. So look at x1, x2, xn. Okay. So these are so these were defined as follows. So I should say this is the Heka algebra of GLN, the Weil group of GLN fish. The affine Weil group. We already called it W. Okay. The affine Weil group W. So what were the lattice generators? So if you remember, so what have we done here? We have just replaced G check by the lattice generators. Okay, so the Xi's can be written in terms of G check and these other TIs, and the equations are this. So the definition of so observe this sort of enables you to replace. I mean, if you had G check, you'll similarly have X1. X2 is T1 X1 T1, which just means you sort of delete the T1 at the end and sort of move it over to the other side. But now it loses the inverse. So it's T1 G check, and then the rest of them are inverses till you reach T2, and so on. In general, Xk is you start with Tk here, Tk till T1. Sorry, is that Xk plus 1? Xk plus 1 is Tk till T1 G check, and then the rest here are inverses. Okay, so this is how you get the Xk's in terms of the G check. So these were the lattice generators. Now,
Tk plus 1 inverse.
Sorry.
Last term should be Tk plus 1 inverse.
Tk, I think, because
No, Tk is at the front.
Rightmost.
Right hand last term should be Tk plus 1 inverse. No, you just replace k minus 1 by k plus 1.
That should be a k plus 1. Sorry. Thank you. All right now? Yeah.
Thanks.
Yeah. Okay, so these are the lattice generators. Now, the relations amongst these guys. So I missed the Q. So what are the relations amongst all these elements? Now, the X's themselves form a commutative subalgebra. So the X's, they form a commutative subalgebra, which we'll call. So the subalgebra generated by X is just the group algebra of the lattice Zn. So i.e. turns out to be the group algebra of this, which Raghavan called C of X plus minus. Okay, so this is just a span, if you wish, the complex span of all X mu's, mu and Zn. Now, so that's the X's. Now, the important thing is to understand the relations between the generators of the affine Heka algebra and the CX. Okay. So these relations, turns out, can be, so the question, so this is the first thing. The next thing to understand is how do the T's and the X's interact, and how does the G and the X interact? Okay. So T versus X and G versus X. So the G and the X is sort of easy. So let's write that down. So G xj G inverse gives you xj plus 1 if I j is smaller than n, and G xn G inverse becomes x1 but with a q inverse. Okay, so it sort of just cyclically shifts the x's, but except when xn goes to x1, it's like that element pi. It gives you this additional factor of q inverse. Now the t with the x's, that's the other important thing we talked about. So the ti, so how do the ti's act? Well, these were the equations that we had. These were the relations. If I and j are sort of far apart, in the sense if j is not I or I plus 1, then they just commute with each other. If this is xi, then when you interchange them, xi becomes xi plus 1. So let me just quickly write these relations out. So I just want to make a couple of points about this. And when you hit t ti with xi plus 1, you get xi ti plus. Okay, so these are the relations which tell you how the t's and the x's interact. Now, so all of this is sort of encapsulated by a single more compact formula, which is, so I should say all of this is encapsulated by a more general formula where, you can also say how ti interacts with the general x mu, and the thing there is that it's x si mu ti. So observe that's sort of the first term here. The leading term in all these cases is of that form, and then plus this additional lower order term, which turns out to be something like this: t to the half minus t to the minus half x mu minus x si mu by 1 minus xi plus 1 inverse. Okay, now so the couple of things I wanted to say about this are the following. Firstly, the leading term. So if you think about just the first term here, then it has the following property. So look at, so these are sort of the first terms. Now the error term, so this is sort of the expected answer when sort of ti moves past the x mu, sort of expect to get this x si mu somehow, and then what's left is somehow of lower order, okay, or it's smaller in some sense. Now smaller in what sense? Well, it's I suppose in dominance order. Is that Arun, is that okay? Is dominance the right way to say?
Yeah, if mu is positive, then the terms will be less. But of course, if mu is negative, then there would be a higher. It's not always smaller in dominance.
Okay, but for I see. So when you say it's the top, so you use the word top term at some point in your paper with Go. When you compute, for example, the leading term of the E mu's, for instance. Right? So I guess those are only for the positive.
Yes. Well, I don't know. I would have to look at the context, but
Okay.
Probably yes. It's only. I mean, the E mu has also this choice of U mu, which is forcing some of the terms to be smaller than others.
Okay. Okay. So in some sense, at least if mu is positive, what you get, so the terms here which sort of come from this additional thing here are all smaller than si mu in some appropriate sense. Okay. So so that's something. So these are sort of lower terms. I mean lower than x si mu. And so that's one remark I wanted to make. Maybe again something to think about during the tutorial. The other point is that these terms will vanish if you sort of take a sum overall. If you symmetrize this. So that's the other remark I wanted to make. If I take not just x mu, but all permutations of mu. So let's take x nu ranges over Sn mu. Okay, you apply all the while group elements. Then if you apply Ti to this, then those error terms vanish. I mean that lower term vanishes. Okay, so let's see this here. So if you'll have, I mean, if you just apply you just take two equations, one Ti on x mu and another Ti on x si mu. So the second term, the error term, will sort of cancel when you apply the other guy. So when you sum over all possible while conjugates, finite while conjugates of mu, then the error term is going to go away. Okay, so that's the other thing. So in other words, Ti times what we will maybe call the monomial symmetric function m nu in the exercise. M mu, sorry. And if mu is dominant. So maybe I'll call it lambda here, m lambda. Okay, so this is the other thing to keep in mind. Okay, now okay, I'm doing much worse on time than I imagine. So let me just point out the third presentation as well. So we talked about two other presentations. Of the Daha. So you take the lattice generators x1 through xn, take t1 to tn minus 1, and you also replace the g by the corresponding lattice generators, so which are now y1 through yn, and then you still have your q. Okay, so again, this is the affine Heka algebra. This again is the affine Heka algebra, and they are sort of related by the involution, which takes ti to ti inverse, xi's to yi's. Okay. And so again, this involves replacing the g by the ti's, but observe that in some sense we already know something. We already know how. I mean, this tells us how the t's and the x's interact. The earlier equation tells you how the g's and the x's interact. So in principle, one sort of knows how the y's and the x's interact. Okay, because the y's are, again, the y's are just given in terms of the g's and the t's, just like before. So the y1, for example, is g tn minus 1, blah, 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 t1. And as before, if you want y2, you push one of them over to the other side. And so the y's themselves are just given in terms of the g's and the t's. So you sort of, in principle, know how the y's and the x's interact as well. Okay, so of course, all this is relevant finally when we talk about the polynomial representation that I have. Okay, so the affine Heka algebra, so that's this bit. So let's call we'll think about the bottom as a affine Heka algebra generated by the t's and the y's. The polynomial representation was the following. You take the affine Heka algebra and you take what's called its trivial representation. Okay, so the trivial representation of the affine Heka algebra is a one-dimensional complex vector space on which the generators act as follows: ti acting on 1. So I mean, it's not trivial in the sense of groups, for example. So it acts by the scalar t power half for I equals 1 to n minus 1, and the element g acts trivial. Okay, so this uniquely specifies how the affine Heka algebra portion acts on the trivial representation. And since we know explicitly what the y's are, so what are the y's? It's g followed by some number of t's and preceded by some number of t inverses. So it's easy to figure out how the y's act on 1. Okay. So in particular, if you sort of say, how does yk act on 1? Well, each of the t's will give rise to a t power plus half, and each of the t inverses will give rise to a t to the minus half. Okay, so in general, this is going to look like t to the, so let's look at the minus halves. There are k minus 1 minus halves, and then there are n minus 1 minus of k minus 1 plus halves. This is a net scalar. So many plus t to the plus halves and so many t to the minus halves. And this is the quantity that this tells you how the y's act. Okay, and if you have seen these, I mean, these numbers seem somewhat familiar. They are exactly what appears when you try to calculate the Y vector, the element rho of GLN. So quick remark here, if you recall rho, the Y vector is half the sum of the positive roots case of GLN. And if you sort of see what this works out to be, these are exactly the coefficients. So it's n minus 1 by 2 is the coefficient of epsilon 1. Then you sort of go n minus 3 by 2, epsilon 2, and so on. The last guy is minus of n minus 1 by 2, epsilon. So the y vector of GLN has exactly these as its coefficients. So if you wish, this is nothing but rho epsilon k. Okay, so anyway, that's the trivial representation of the affine Heka algebra. And what is it that we want to understand? So, okay, what's the polynomial representation itself? So recall from what Raghavan mentioned, the polynomial representation is just, I mean, you can think of it as Cx plus minus. So it turns out to be what you get when you induce from the affine Heka algebra to the Daha itself. When you take just this trivial representation of the affine Heka algebra, you induce it from this subalgebra here, from the y's and the t's, from the aha to the daha. Okay, and that's your induced representation. And as a vector space, it's just the space C of x plus minus. Okay, so it's the Laurent polynomial ring in those n variables. And recall also from what Raghavan said that we sort of know how the elements G's and Ti's act. So we sort of want to know how does the AHA act, the AHA action of this. In other words, you want to know how Ti's and G's act. So the G action is given as follows. It just permutes the xi's. So you take x1, x2, xn, but then you move the variables around, mu1, mu n minus 1, mu n, and then there is a power of q in front. So it sort of permutes the xi's, cyclically permutes the xi's, and there's a power of q as well. And the action of ti's is given as follows. So let's just write this out as, so how does ti act on a polynomial so if I take f of x, so how does ti act on f of x? Well, it's on the one hand, it's some multiple of fx, but then there is a difference operator. So it's this into, so it's f of x1, x2, xn minus f of x1. So you interchange the variables xi plus 1 xi, xn by xi minus xi plus 1. So observe that this quotient that we are forming here, so you take f and you take f with the variables I and I plus 1 swapped, then you divide by xi minus xi plus 1. So it's of course always going to be divisible, and then you multiply by a degree 1 homogeneous term. So observe that the action of ti, if f of x was a homogeneous polynomial of some degree, this is going to give you another homogeneous polynomial of the same degree. Okay? And same with g. G again just also permutes these. So what again this remark was made that this action ti and g, they preserve degrees. So the action of ti and g preserves degrees. So homogeneous polynomials of, if f is homogeneous of degree d, then so is gf and tif. And the other thing it preserves is the positive part, in the sense, not the Laurent polynomial ring, but if you just take C of x1, x2, xn, the polynomial ring is also preserved under the action. Okay, and again, that's clear from the way the definitions are. Okay, and again here, what you know is that we sort of know the actions of T and GI. So what we have are these, but what it implicitly determines is the action of the Y's as well. Okay, now, okay, so let me maybe take another 5 minutes is okay, Venkatesh?
Yes, no problem.
Okay. So let me just say something about the intertwiners that Raghavan defined. So intertwiners are the following. So they were operators on the polynomial representation. Tau I check equals Ti plus so this was I equals 1 to n minus 1. And so the point I wanted to make here was that observe that in some sense the intertwiners themselves are sort of, they only involve operators from the affine Heka algebra. So they only involve Ti's and they involve the Yi's. So in other words, they only involve the Ti's and the G's. So these again have the same property that we talked about, that they preserve, the action of tau I check preserves degree, for example. Okay, because it really comes only from the AHA portion. Okay, and however, there's this other guy which is called tau pi check. Okay, and by definition, this intertwiner tau pi check was just defined to be the element G check. Okay, so observe this is somehow all along we've been talking only about the operators coming from the AHA portion, but this is the first time we are looking at something which also involves the x's, the C x's. So the other intertwiner actually is G check, and if you remember how G check was defined, this is you can write it in terms of x1 as follows. So if you rewrite G check in terms of x's and the t's, then you realize that it's actually x1 t1 t2 tn minus 1. Okay, and this intertwiner therefore does not preserve degrees. These guys of course preserve degrees. X1 will increase, you're multiplying by an x1. So what it's going to do is it's going to increase degrees by 1. So this intertwiner increases, it still maps homogeneous guys to homogeneous guys, but it increases their degrees by 1. Okay, so in some sense, it's like pi, morally like pi. It sort of changes the degree by 1. Okay, and what we also observed, so what Raghavan pointed out, that not only can you define tau pi check and tau I check, you can define tau W check for any W in the affine while group. So even tau W check makes sense. In the affine while group, and therefore, if you sort of see how does okay, so what was the final definition? So maybe I should just recall the definition of the non-symmetric Mcdonald polynomials. So the emus themselves were defined as follows. There's a certain prefactor, some power of t here, which is used to normalize the coefficient. But what this is you just apply this tau corresponding to the element u mu that we talked about at the beginning on the element 1 in this is the element of the polynomial representation. So this is some element of the Laurent polynomial ring. But as we just said, because the element 1 is in fact it's positive, it's got positive degrees here. Oh, okay. No, I can't say that just yet. Cx plus minus. Okay, so so this was the definition of the emu itself. So the point I want to make about this is that observe that each time you apply a pi, so what is this going to look like in general? So there are going to be some u mu, if you remember, was the box greedy word that I talked about in the beginning. So it's a string of pi's and si's, and each time you have a pi, so there's maybe pi and then there's an si. There's a pi again, a bunch of si's and so on. So each of these pi's, when they act on 1, they'll increase the degree by 1. Okay, whereas the subsequent tau I checks, when they act on whatever you have, they don't do anything to the degree. Okay, and so on. So if you sort of see what's the final degree of the resulting polynomial, it's Well, it's equal to the number of pi's that you encounter as you scan the box greedy work. Okay, so the degree of this guy, and if you remember, so this is just the number of pi's occurring in U. Okay, but how many pi's occur? So if you remember what we started out with right in the beginning, each time you apply a pi, it sort of increases that. I mean, if you remember our example, we had 0, 0, 0, you apply a pi and you get a 1. You apply a pi again, you get another 1. So the total number of pi's in that example was actually 1 plus 2 plus 3, the total sum of all the parts. So this is in general just going to be the sum of all the mu i's. So what you are constructing here is actually a homogeneous polynomial in the xi's, xi plus minuses in general, whose total degree is mu I. Okay, so that's one thing I wanted to say. So I guess I'm already way over time. So I don't know. Maybe I should stop and sort of continue from here. So I was hoping to get to the definition of the symmetric Mcdonald polynomials, but I guess I underestimated the time it will take me to get there. So should I stop, Venkatesh?
No, it's up to you. How much time you need?
I guess another, maybe I can just very quickly give the definition alone. Is that all right? That will take me maybe another 5 minutes.
Yeah, that will be fine.
Okay. Okay, fine. So to define the p mu's, the symmetric Mcdonald polynomials, so just say symmetric. So what one does is you just apply. So let's take lambda, maybe call it lambda. So on. So you first look at E lambda. So E lambda, the non-symmetric Mcdonald polynomial, which is this appropriate power of t tau u lambda check 1. And to this we apply the symmetrizer. So there's this element in the finite Heka algebra. So we call this H finite. So this is sort of the symmetric idempotent, or call it symmetrizer maybe, defined as follows. This is, it's the sum over all this is just all elements of the finite Sn, okay, just generated by T1, T2, Tn minus 1. So this element then, can sort of put a normalizing constant in front. So I think minus length of the longest element by 2. So if you take this element, this is actually in the finite algebra. Okay, so this, in fact, this affords the trivial representation. In other words, if I multiply Ti on 1, 0, this just gives me t to the half. Okay, so this is the symmetrizer. So I think Arun calls this the bosonic symmetrizer in his notes. So there's also the symmetrizer with signs, the anti-symmetrizer. So you just take the symmetrizer and you apply it to the non-symmetric method. So you just take this element 1, 0 and you apply it to lambda. Okay, and there's some normalization again that's required in order to get the coefficient of the corresponding monomial to be 1. So this is the definition of E lambda. Okay, so what this actually involves is you take E lambdas, and then essentially what you're doing is you're applying the finite T sigmas to it, the elements of the finite Heka algebra. This is an essence. Then there's a normalization here. So W lambda here is the stabilizer of lambda, the Poincare series of the stabilizer. Okay, so that's the definition itself. So maybe I'll talk about the properties and so on next time. So firstly, it's symmetric, and again, analogous to how we talked about the non-symmetric Mcdonald polynomial as the simultaneous eigenvectors for the yi's. These turn out to be the simultaneous eigenvectors for all symmetric polynomials in the yi's. So you have an analogous way of thinking about it in terms of the yi's, but only in terms of symmetric polynomials in the yi's. Okay, I'll stop here.
Can you go back a minute to the previous slide?
The previous one?
Yes, thanks.
So what is the symmetrizer? I'm a bit confused. So you take, you act by sigma on lambda. You
Sorry,
permute
just a second.
lambda in all possible ways.
Can't hear you too well. Sorry, say that again.
Sorry, I was just asking. I'm not understanding this 1-0. So it's action of sigma on lambda.
No. This is acting. So these are the T sigmas. So they are going to act on Cx. See, this is an element in the finite Heka algebra, if you wish. So the finite Heka algebra has an action on the polynomial representation, right? See the TIs, for example. So we know how the TIs act on the X mu's via those operators.
Yeah.
So the general T sigma is a product of TI1, TI2, TIk. So that has a certain action given in terms of those operators on the polynomial representation.
Okay, so you take all possible product of T sigma i's and then you sum over all possible sigma up to sigma.
Correct. You sum over all possible sigma and then you act on the E lambda of X. I mean, the action is then on the non-symmetric polynomial.
Okay.
So the last line in the previous slide is the relation that holds in the finite Hector algebra. Once you define one.
Correct. This is the trivial representation, if you wish, of the finite Hector algebra.
This is actually a representation.
Correct. I mean that
because it
1 0 is, yeah. I mean, you can think of it like that one dimension.
Because of this relation, you can think of it as a
So 1-0 also has a t to the power minus L W naught by 2, and P lambda also has a that thing in front.
Plus.
Yeah, I don't know why. So in some sense, when you apply, so that's a minus and this is a plus. So this is, so I mean, you don't have that term when you apply it on. So Arun, why do you have this term for the?
Only to match the normalizations of Mcdonald.
Okay, that Mcdonald has, I see. Yeah, so if you wish here, this t to the L lambda by 210 is just, essentially without that term, if you wish. Yeah.
Can you go one slide back? Yeah, here you have mu dominant or anything?
No, mu anything. This should work for all.
But so summation, okay, but mu i's are greater
when I say
0?
pi's, I guess there is also pi inverses which are possible, right? When you apply, so when we did this box 3D, I mean, if mu's are negative, for example, then we'll have to apply pi inverse instead of pi.
Right. Yeah.
So for a general mu, you're also looking at pi inverses.
Yeah. Okay.
Could you go back one slide, Viswanath, please? Sorry, maybe forward.
Forward? Yeah.
One more. Yeah, this last equation, so the previous one, please. Yeah, so this last equation, I'm a little confused. So this is not in the Heka.
This is in the Heka algebra. So if you multiply, so what we are saying is you take this element, you multiply, so you'll have to look at what happens to things of the form Ti T sigmas. So if the length goes up, then it's just T of SI sigma. If the length goes down, then you will get that term plus this additional T sigma term. Right? So you're sort of looking at.
I see. So this is in the Heka algebra. This is in the Heka algebra itself.
It is in the Heka algebra itself. Yes.
Ah, okay. Okay, thanks. Yeah.
Any more questions or comments?
So I have a quick question. So this your presentation 2, I'm a bit confused between that and this representation that you're talking about. I mean, somehow it should I don't know. Morally, it should have been done the other way, right? I mean, we are acting by the y's on these xi's, right? To get these non-symmetric Mcdonald polynomials, right? So is that, or am I getting confused?
Sorry, I didn't quite understand your question. So what do you mean presentation?
Sorry, it's not very well posed. I'm just asking, I mean, presentation 2 could have been done equivalently using, I mean, replacing the y's downstairs and keeping the g check upstairs, right? I mean, it's the same thing.
No.
Because of the involution.
Yeah, that's true. But finally, what we are for, see, the polynomial representation itself involves thinking of this as your subalgebra, the affine Heka algebra inside your.
Yes, but you want, but that's precisely what I'm asking. So don't you want to think of that affine Heka algebra inside involving the xi's rather than the yi's?
You mean you're saying shouldn't we think of this as your affine Heka algebra? Yeah. And then is that what you're asking?
Yeah, or am I misunderstanding something?
No. So see,
because we're acting on the xi's, right? Eventually,
you're acting on the xi's eventually, but what you're doing is, see, this definition of this induced representation is like saying, okay, here's what it was, right? So what this says is the following: you start with the trivial representation of the affine Heka algebra. What does that mean? You just have a one-dimensional space.
Yeah.
Right. This C1, we called it. So here's a one-dimensional vector space, and on this one-dimensional vector space, the action of the y's and the action of the ti's is given. They all act by some eigenvalues. Right? They act as some scalars. Then the induction process is like saying, okay, now I just sort of induce this to the entire DA.
Yeah.
Over this. Okay. Now, what is the resulting space? In some sense, see, the Daha itself is, you've got the x's. So think of it as there are the x's, and then there's the affine Heka algebra. So I'll just write this loosely like this. So there's the bunch of x's and then the affine Heka itself. Right? And then the point is the affine Heka algebra action is sort of known. They act trivial. Right. So what's left is, in some sense, the action. I mean, it becomes this free, the Laurent polynomial ring, C of x plus. So, so in some sense, when the final answer that you want, when you say that that's Cx plus minus, what you're doing is you're sort of killing the y's. The affine Heka algebra portion acts trivially on that. I mean, it acts in, via the trivial representation on the one-dimensional space. And sort of the leftover degrees of freedom are really your Cx plus minuses.
But I thought you precisely want to do it the other way around, because you want to act by the yi's to generate your.
No, so the point is, on this resulting module, see, the final object that you get, this guy has an action of the entire Daha. Right? So you started with the subalgebra induced upwards, and then on that guy, the entire Daha acts. So what you're trying to understand now is, how do the yi's act? I mean, your original generators whose action on this one-dimensional space you understood, but after induction, you now want to ask, oh, how does it act on this big space that I get as a result?
Okay.
So in fact, Arun has it's one of the things that I want to talk about eventually. So you for example, this is the natural question. So Cx, which is you induce from here to here, the trivial representation, and then the natural question is, well, what happens if I restrict that back down to the affine Heka algebra? How do the TIs and the YIs act?
So there's no Frobenius reciprocity here, I suppose.
Frobenius reciprocity wouldn't apply, I guess. No. So what I mean?
This is not trivial,
basically. Yeah. So what you want to understand is, what are these spaces? So for example, what are the submodules? Which subspaces of Cx are invariant under the action of the Ti's and the Yx. So one thing you already know is that the non-symmetric Mcdonald polynomials are going to be invariant under the Yx because they are eigenvectors after all. Right? But the Ti's are not necessarily going to leave. How do the Ti's act on your E mu's? Will you get back? They're not going to act as eigenvectors. Right? But it turns out that, well, what you sort of get is something in the span. You sort of get E SI mu, right? And in other words, the span of the Weil conjugates of E mu, all the reorderings of E mu, that space is however invariant under the TIs as well. So there's this thing which I'll probably talk about next time, which is you can for each lambda you sort of split it into this space. So that space is invariant under the Y's as well as under the TIs. So it's an answer to this question, right? I induce up, and then what do I get when I restrict it back down to my original algebra I started off with?
Right.
Okay. So what is the CX lambda, Viswanath?
CX lambda is, I think, the span of all the EW lambdas, all the reorderings. Is that right, Arun?
Yes, that's right.
So the point is, the Y's will leave them invariant, of course, but the T's will sort of move them around. The TI's, when they act on a given E mu, they will give you, E SI mu. So there were a bunch of different cases and so on. But essentially, the span of this space is going to be invariant.
But this equality, this is an equality you are saying, but each of those is invariant or something, or what?
Sorry, ask that again.
So Cx is equal to the direct sum of these guys.
Correct.
You're just grouping them according to Sn and then the rest of it.
Correct. And
so here lambda runs over what? Just any
lambda is over all lambda 1 greater than or equal to lambda. But this is Zn, lambda in Zn.
But Zn in the increasing order or something because of this.
Yes, Zn in decreasing order, let's say.
Yeah, decreasing order, right. And you're saying each, and so what about each summand here? Each summand here is invariant.
This is an HF module.
Each summand is an HF module, right?
HF module, yes.
There's no pi. Okay.
And I mean, in some sense, the symmetric Mcdonald polynomial is going to lie here. It will live in this space. The corresponding, because what did we do? We took an E lambda and then we applied the various finite T sigmas to it.
Perfect.
So this space Cx lambda certainly contains the P lambda.
Perfect. Thank you. That's very good.
So I have another kind of philosophical question. So from the way you defined it, I mean, in all these presentations, you have different number of generators, right? So somehow from that point of view, it's not so surprising that, all these xi's and commute with each other and all these yi's commute with each other, right? Because you're replacing one single G, or G check by these xi's. But on the other hand, I mean, from the way I was describing it, it seems like a miracle that all these operators commute. So I mean, what's the sort of resolution? I mean,
I think probably yes.
I mean, in general, if I give you some algebra, like the group algebra, the symmetric group, and I say, find me n commuting elements simultaneously commuting, it's not so easy. So, and the same thing has happened here. Of course, a posteriori, it's trivial that they call commute, but if I just give you the Daha and ask you to find me y1 up to yn, which all commute, is not so.
I mean, those formulas which define the YIs, for example, I mean, yeah, if you just look at those formulas, it doesn't at all seem clear that the commute things. So, I mean, could one just actually write them out? I was trying that just before the thing. If you actually write out x1 times x2, those inverses and TIs in the preceding and succeeding, somehow they should all cancel out to show that the answers are the same. Is that even that didn't seem that obvious? I mean, it involves one of the relations, etc.
So when you say give the Daha, you mean give the first presentation in terms of G and G check, and then you say find n commuting operators.
Correct.
That's not going to be easy.
Yeah.
But a posteriori, when you see the xi's written in terms of G and Ti's, then you maybe after some computation.
Yeah.
So in terms of suppose, I mean, from the while group to the from the affine while group going to the Artin group, for example. So how does one? I mean, this formula for the x epsilon 1 that you write down, is that something that you can deduce by just looking at the corresponding situation in the while group?
Yes, if you do it carefully, it's better to think if you start with the Artin group and then put Ti squared equal to 1, you will recover the Weil group, the double affine Weil group.
Right.
So.
Okay.
Okay, let's thank Viswanath.
Yeah. So I think next Wednesday is not, it seems to be holiday.